All right, so we have come to section 4.7. This is about optimization, and I've talked about optimization a little bit before, back when we were in the beginning of chapter 4, when I was explaining like maximums and minimums and that closed interval method. We actually did, I think, an example of an optimization problem way back then. But this section, we're going to dive into it in more detail and with some more challenging problems. In general, optimization is just finding a maximum or minimum value of a function on an interval or on some domain. All right, that's in general all it is. We've basically already studied how to do that. The thing is, now we're going to do that in context, right? So now we're going to look at specific applications with specific functions modeling specific like useful real-world scenarios, and then apply the maximum and minimum finding strategies that we've learned to those scenarios. So the first example I want to deal with here is this sort of interplay for three-dimensional objects, interplay between surface area and volume. So suppose you've got a box, right? And this idea I'm going to describe here works for any three-dimensional object. But let's just talk about a box to make it simple. And in particular, I've drawn three boxes that are like open boxes. There's no lid to these boxes. The first problem we're going to work on is an open box problem. So suppose you've got a box. You can vary the width of that box down at the bottom here. You can make it like a narrow box like this, or you can make it sort of medium, or you can make it like a wide box. So that base, and also in this instance, I'm kind of thinking about the base being square, but yeah, so you can have like narrow boxes, or you can have a medium sort of sized box, or you can have like a large wide box. But if you're going to fix the surface area, which would be like the four sides plus the base, okay? If you're going to fix the surface area of the box, then when you make your box narrow, you also have to make it tall. And when you make your box wide, you also have to make it short. So if you increase the width, you've got to decrease the height in order to like accommodate that increase in surface area on the base. You've got to decrease the surface area on the sides, right? So that it all ends up still being exactly the same surface area. And so you have this range of situations, and what happens is, in the extreme values, when you have a very tall, skinny box, you actually have a small volume. And when you have a very short, wide, like shallow box, you also have a small volume. And somewhere in the middle, there's a sweet spot where you have a maximum volume. So when fixing surface area, if you allow the other dimensions like the height, width, and length of the box to kind of vary, then there's gonna be some like range in values for volume between small and big and then small again. And so the optimization problem would be fix the surface area and then try to figure out what dimensions are going to give you the maximum volume, right? I've drawn this picture for you to help you understand this idea. But I challenge you to turn this around and think about the situation where you have a fixed volume, and then you allow the parameters, the dimensions of the box to change, and kind of think about different extreme situations. With a fixed volume, what's going to happen with the surface area? Okay, are you going to have big, small, medium? Like, how is the surface area going to vary as you change the dimensions? Okay, that is another type of optimization problem you can do. So, in the first example, we'll go ahead and have surface area fixed at 108 square inches. Okay, so let's say that's our fixed surface area. Now we're gonna make we normally for an open box, this is going to be an open box. You have like the width of it, the length, the width, and the height. You normally have three different dimensions, and that would be a bit complicated. With three dimensions, you might have to make a function of multiple variables. But what we can do to kind of simplify this down a little bit is we can assume that the base is square. If the base is square, then whatever dimension this is also equal to that amount. So the width and the length of the base here are both equal. The height can be different, Okay, and that's kind of the picture that I drew here. I'm imagining this is x and this is also x. That's x and that's x, that's x and that's x. And then the height is changing to accommodate the change in x and ensure that the surface area is always constant. So the question is then going to be, what is the maximum volume that such a box can contain, given this what we call a constraint? This here is our constraint. And actually the base's square is also another constraint. So I'll put an S on the end of that. Those are our two constraints. Okay, without those constraints, we would have too many variables and we wouldn't be able to really solve this problem with calculus 1. We'd have to be using calculus 3 strategies. But with these two constraints, we're going to be able to get a function that tells us the volume as a function of one variable, which I think we're going to do it with x here. So the textbook introduces some vocabulary here, which talks about a primary equation and a secondary equation. So the primary equation is the equation that describes the value, like the quantity you're trying to optimize. So in this problem, the primary equation is the volume equation. We're trying to find the maximum volume. So the volume equation for this box, whenever you have a box like this, the volume is going to be given by the area of the base down here, the area of this base, and then multiplied by the height. Okay, so this is going to be x squared times h. Another way to think about it is just multiply width times length times height. Three dimensions multiplied together gives you volume. So that's our primary equation. That's the one we want to optimize. But the secondary equation is basically the constraint equation. It's the equation that has something to do with it, basically expresses your constraints over here. And in our case, that secondary equation is that the surface area has to be 108 inches squared. So let's write a second equation to calculate surface area. We're going to have the base, which is going to be x squared. X times x will give us the area of the base. And then you've got the four sides, because there's no top. Okay, this is a box without a top. So we just have 1, 2, 3, 4 different sides. And those sides are actually all the same area because they all have a base. They're all a rectangle with a base of length x and a height of length h. So I'm going to write plus 4xh. Okay, so that's the base of the box and then plus the four sides. Adding up all those areas is our surface area, and so that has to equal 108 due to this constraint. So we have our primary equation and our secondary equation. Now what we're going to do is take the secondary equation and solve it for one of these two variables and do a substitution, thereby eliminating that variable from the primary equation. So what I'm going to do is I think the easiest here is going to be to solve this for h. So we're going to subtract the x squared from both sides, divide by, so to subtract the x squared and then divide by that 4x to cancel that out, and we've got h. And so now that is going to go in there. So now the function we get to work with is v as a function of x is going to be x squared times 108 minus x squared over 4x, like that. And we can simplify that a little bit. For one thing, one of the this x in the denominator is going to cancel with one of these two x's. So that's nice. And then for another thing, the x can be distributed through here. The x we have left over, we can multiply that through here. So let's write that as 1/4 times 108x minus x cubed. There we go. That sounds pretty good. Okay, so now before I go on, let's stop here, pause here, look at this function, okay, v of x equals this here, and ask what's going to be the reasonable domain we should use for this function. This is a cubic polynomial function, which means that it is kind of like in theory, this function has a domain of all real numbers, right? Like if there were no real world context to consider, we'd say the domain of that is all real numbers. However, there is a real world context, so there's only a certain domain of x values that is going to make sense in this situation. And so to figure that out, we're going to look at the extremes. Extreme situations. So on the one end, we could have a very, very small x value, which I'm going to try my best to draw an open box with an extremely small x value. You barely even see that. So x would be really little, right? No matter how small you make x, you can make your height bigger and bigger and bigger. Like we can make this x tiny and then have the box be like as tall as a skyscraper. And it would still, I mean, we could still set it up so that it has a surface area of 108 square inches, which is kind of a silly thing to imagine, but it's possible, right? So we're going to use as our low end, x equals 0 is a minimum, x. So x equals 0 is going to be our low end. Now on the high end, what if we have a really, really big x? Let's draw that. Let's say that's our x. It's really, really huge. Well, then it's got to be this direction as well, right? So our box, in order to keep the surface area at 108, we're going to have a tiny, tiny, tiny h value, right? So it's going to be like, it's like this. This is now, I mean, I barely even call this a box. This is more of like a very shallow tray or whatever, right? So h is going to get really, really small. But the surface area still has to be 108 square inches. Now what that means is you can't have x approach infinity, because this base, right, this sort of base down here, right, the base of this box here, this area can't exceed 108. If x gets large, h can approach 0. So let's kind of assume for our extreme situation that the sides of this box have negligible surface area, which means that it's so small that it doesn't even matter. Like it's approaching 0 surface area on the sides. So the entire 108 square inches should be taken up by the base, which is just this rectangle. It's a square, actually, because it's x by x. So what x value would achieve that? Well, if it's a square of area 108, the x value, the side, is going to have to equal the square root of 108, and that is going to be our maximum x. So for this function, we're going to use as our domain the interval 0 to the square root of 108. Okay, and that gives us the fact that we now have this closed interval to work on means that we can now use the closed interval method to find the maximum value of this volume function. So I'm going to stop the video there and then finish this problem in the next video.